Okay, so think about this. We're surrounded by glass every single day. It's in our windows, our phones, our kitchens, and we all know what happens when you drop it, right? It shatters into a million pieces. But here's the crazy part. For decades, scientists had no idea exactly why. It's been this massive mystery in materials science. Well, today we're finally cracking that code.
When you look at a shattered piece of glass, what do you see? It looks like pure chaos, doesn't it? Just a totally random event. But what if it's not? What if, hiding underneath all that apparent randomness, there's a secret, predictable pattern to the collapse? Well, that's exactly the question scientists have finally managed to answer, and the answer is going to blow your mind.
All right, so to really get this, you got to understand that there are basically two kinds of solids in the world. On one hand, you've got crystals. Think of a diamond or even just table salt. All their atoms are lined up in this perfect, orderly grid, kind of like a neat stack of Lego bricks. We've known for ages how they break. Tiny little mistakes in that perfect pattern, called dislocations, just kind of move through it. It's pretty predictable. But then you've got glasses, and they're the total opposite. Their atoms are just a jumbled, chaotic mess, like someone dumped out a bucket of sand. And because of that chaos, figuring out why they break has been a complete mystery for, well, forever. Until now, that is.
Okay, so let's start our investigation. For years, scientists had only one suspect in the case of shattering glass, this mysterious thing they called soft spots.
So the theory went something like this. Inside that jumbled mess of atoms and glass, there had to be these little areas that were just weaker or softer than the rest, and that's where a failure would kick off. Sounds logical, right? Well, here's the catch. Nobody could actually define what a soft spot was. You couldn't point to it, you couldn't describe it with math. It was basically just a placeholder, a name for a ghost in the machine that nobody could prove was actually there.
And then, the big break in the case. The breakthrough came when scientists had a radical idea. What if we stop looking at the atoms themselves and instead look at the invisible forces between them? And when they did, they found something absolutely incredible. These hidden, swirling patterns of stress.
They gave these patterns a name, topological defects. Now, this is where it gets a little weird, but really cool. A defect here isn't a physical thing. It's not a tiny crack or a missing atom. It's a purely mathematical pattern. Think of it like a tiny, invisible whirlpool swirling in the field of forces holding the material together. It's a ghost that you can describe perfectly with math. It's a pattern, not a particle.
And it gets even better. These defects come in two opposite flavors, kind of like the north and south poles of a magnet. You have the vortices, which have what we'll call a positive +1 charge swirling one way, and then you have anti-vortices, with a negative -1 charge swirling the other way. And trust me, this whole idea of positive and negative charges, it's going to be absolutely key to solving this mystery.
All right, so now scientists can actually see these defects, and the obvious thought is, well, the more of these little whirlpools you get, the weaker the material becomes, and eventually it just breaks, right? Makes perfect sense. Except that's not what happened. The data showed something completely unexpected, a real twist in the story. Okay, you gotta follow this because it's pretty wild. So you start putting stress on the glass, you're stretching it or bending it, and just like you'd expect, the number of these topological defects starts going up. The whole material starts filling up with these little force vortices. But then, at the exact moment of failure, the thing that actually makes it break, the defects don't cause the break. They massively annihilate each other and just poof, they vanish. Get this, the failure isn't caused by the defects showing up. It's caused by their sudden, catastrophic disappearance. Mind-blowing, right?
And look, this isn't just some wild idea. It is backed up by some serious data. The Pearson correlation coefficient, which is just a fancy way of measuring how two things are related, is -0.5. Now, in the world of statistics, that's a really strong signal for what's called anti-correlation. It basically means when one thing happens, the other thing does the exact opposite. This is the statistical smoking gun. It proves that when the failure happens, the number of defects plummets.
So, this incredible discovery just narrowed our search. We now know it's the annihilation of defects that matters. But are all defects created equal? Or is there one specific type that's the real trigger? The hunt for the main culprit was officially on. And the research paper itself gave us the next big clue. The scientists found what they called a prevailing bias towards net negative charge values. So what does that mean in plain English? It means the material wasn't just creating defects randomly. For some reason, it was specifically building up an excess of those anti-vortices, the ones with the negative charge.
And that was the final piece of the puzzle, the real smoking gun. The thing that actually predicts a failure isn't just any old defect. It's the formation of large clusters of defects that, altogether, have a powerful net negative charge. These clusters, these are the soft spots scientists were hunting for all this time. We finally found them.
And just look at this data right here. This is the proof. The table shows the number of these big negative clusters right around a failure event. So before the first failure, there are 11 of them. But at the exact moment of failure, bam, the number drops to 6. And check out the second event. It's even more dramatic. It goes from 11 all the way down to 3. This is it. The evidence is undeniable. The failure event is the sudden disappearance of these clusters.
This spectacular, violent event even has a name now. They call it a topological avalanche. And it's a perfect name for it. It's this sudden, massive chain reaction where those big negative clusters just collapse and fragment all at once. It's not a slow crack spreading. It's an instantaneous, system-wide avalanche on a microscopic scale that we, out here in the real world, experience as a shatter.
So there you have it. The verdict is in. The case of the shattering glass is officially closed. But you know, solving this mystery doesn't just close an old chapter of science. It blows the doors wide open for a whole new era in engineering and technology.
So let's just recap the solution to the whole case. Those mysterious soft spots that haunted scientists for decades? Well, they're not a myth. They are large clusters of defects with a net negative topological charge. And the big twist? It's their sudden, massive disappearance, that topological avalanche, that's the real trigger for the material breaking. The mystery is solved.
So why is this such a big deal? I mean, who cares, right? Well, it's a huge deal. Because for the first time ever, we can potentially predict where and when a disordered material like glass is going to fail. We can finally move past just guessing and hoping a material is strong enough to actually designing new materials like stronger metallic glasses or tougher plastics. We can engineer them from the atoms up to resist forming these negative clusters in the first place, making them way, way more reliable.
It really makes you wonder, doesn't it? If something that looks as random as shattering glass is actually governed by these beautiful, hidden mathematical rules, what other parts of our world that seem chaotic are just following a deeper, invisible structure we just haven't found yet? I'd love to know what you think down in the comments. And hey, if you had fun cracking this code with us, do us a favor and hit that like button and subscribe for more deep dives into the secret rules that run our universe.